galaxy morphology and the correlation with black hole activity. And to do so, I'm using the IllustrisTNG simulation. So I think one of the biggest challenges that we are facing when trying to understand galaxy buildup is the formation of the massive quiescent galaxies at low redshift. So observation at redshift 2 and higher has revealed two different populations of galaxies. The first one, yeah, it's really fun. Okay, the first one is star-forming galaxies. Star-forming galaxies over there, which are just like morphology, irregular or clumpy, with a really high star formation activity. So in this diagram, I'm showing. Is there another pointer or something I can use? No, I think it's too faint. Sorry. So we have this superpopulation of galaxies that we observe. So star-forming galaxies, so they're on the upper left panel of this diagram by Barrett 3 years ago, and extending galaxies. So on the left, on this sigma relation. Sorry, thank you. Oh. Well, I can do it. We have quiescent galaxies, which are more compact galaxies, but also really massive and very suppressed star formation rate. So a natural way of seeing this picture is to think about a transition path between this superpopulation of galaxies, and that's what it was observed in this paper with this population of compact star-forming galaxies here, and we call them blue nuggets. So basically, we can think in terms of a path between those three populations of galaxies. And a really nice theoretical way of seeing this has been summarized by Zolotov in this picture. So it's a summary of zoom-in cosmological galaxy simulation with this transition path between the star-forming galaxies to quiescent galaxies. And what we see is that the stellar content of the galaxy is increasing with time. The gas content of the galaxy is also increasing with time, but at some point you reach a peak, which also corresponds to a star formation activity peak, and after that you really decrease strongly with time the mass content in the inner regions of the galaxies, and we call this quenching. So you have compaction and quenching. So this is the big picture, and we will come back on this in a minute. So more important, what we have observed in the few recent years is a correlation between the part of the diagram, the specific star formation rate, compactness diagram, and the activity of black holes. So we have heard just like before that you can have a really high fraction of Asian in the star-forming compact galaxy part of the diagram. So this is a Sesky paper. And another interesting paper is the Shang et al. Paper last year with this picture. So they try to identify Asian, obscure Asian in star-forming galaxies. And what they find is that the hosts of obscure Asian have smaller radius compared to normal star-forming galaxies. So the more the activity of the black hole is, the more compact you are. What we want to do with this new run of Illustris simulation is to follow and to study the galaxy population in the simulation as well as the black hole population. So I will talk about this. We also want to derive the Asian fraction in the different parts of the diagram, of the specific star formation rate compactness diagram. And as an overall goal of this is to study the Asian impact on quenching galaxies and also maybe on impacting the morphology of those galaxies. So IllustrisTNG is a new run of Illustris. It's now done. So it's composed of three size simulation from 50 megaparsecs to 300 megaparsecs on the side. So this is one of the code repo. So you have all the physics that large-scale simulation normally have. So you have primordial and metallic cooling, star formation in dense ISM. So those stars are able to enrich the surrounding gas. You also have supernova feedback, which is a new feedback compared to the old simulation. You have black hole formation in massive halos. And those black holes are able to grow in mass by accretion of gas, but also mergers with other black holes. And you have a new agent feedback, which is composed of two modes. The first mode for highly accreted black hole is a quasar mode. And then you have another mode, which is a kinetic wind mode for low accretion right into the black holes. And you can find some interesting routing in this paper. So here are the two different resolution of the simulation. And for this project, we use the two largest box. So this really large box of 300 megaparsecs on the side is really useful because we know our statistics on massive galaxies, and we can also compare with the intermediate box for resolution effects. So what we have done is to first selection galaxy according to their morphology. So we first do a selection in star-forming galaxies. So to do so, we wanted to have something which is redshift dependent, but also simulation dependent. So what we do is to look at the star formation rate as a function of stellar mass for all galaxies in the simulation. So the gray dots here. And what we do is to fit the main sequence of this galaxy below 10 to the 10 in solar mass to avoid the contamination by quiescent galaxies. And we follow Brennan et al. Recent paper. And if a galaxy has a star formation rate higher than 20% of the main sequence, we consider it as star forming, and otherwise quiescent galaxies. So it gives us a redshift and simulation dependent selection for star forming galaxies. And we also need to select galaxies to know whether they are compact or not. So there are many thresholds in the literature to do that. So here I'm showing you the mean evolution of the size of galaxies in the simulation as a function of stellar mass with redshift, and all the dashed and solid lines are different thresholds that have been used to define compact galaxies. So instead, what we are doing here is to do also something redshift dependent and simulation dependent. So we divide the sample of galaxies into the galaxy population in two different samples, whether they are star forming in blue or quiescent in red. And we also derive the mean evolution of those two samples, and we fit this. And if a galaxy is, if the size of the galaxy is 50% higher than the mean size galaxy mass relation, it's considered as compact, otherwise as extending galaxies. So here, I have to say that it's not a really objective threshold. It's just to select the most compact galaxies. So you have different ways of selecting this. I only consider the most compact galaxies, but we try a different selection based on sigma on the surface density, and it doesn't really, it selects more compact galaxies, but it doesn't affect the result on the agent fraction that I will show you. So now what we can derive is the number density of compact galaxies and quiescent galaxies with time. So here I'm showing you the compact galaxies star forming in red, and in yellow the quiescent compact galaxies for two different cuts in stellar mass. So what we see is that we first have a high level of star forming compact galaxies, and then this drop in time, and the peaks is at redshift 2 or so. And for the quiescent galaxy, we start really low, and then we keep increasing until redshift 0. And for more massive galaxies, line cross at higher redshift. So the turnaround is at earlier time. So this tends to say that indeed quiescent compact galaxies can have for progenitor star forming compact galaxies. So here I have to say that if you're familiar with this kind of diagram, normally the normalization is a bit higher, but here I'm selecting only the most compact galaxies, so that's why I have less galaxies. But this is consistent with all these papers. Because I will show you the agent fraction in this different part of the diagram of the specific star formation rate compactness diagram, I first need to show you the black hole population in IllustrisTNG. So in the term of black hole mass as a function of stellar mass, the simulation does a very good job at reproducing as different observations. So here's a sample of Amy, Rance, and Marta Voluntary 2 years ago. So you have quiescent galaxies as a white triangles and more agent-like galaxies as a black triangle. And what we see that the simulation in blue cover all those different galaxies, which is good. However, when you look more carefully at the accretion properties into the black hole for the new simulation, we have some caveats. So this is the bolometric luminosity function as a function of bolometric luminosity, and you have the same for black hole X-ray luminosity function. So the different gray lines here and here, the two lines, are from observational constraints, and the colored line are the simulation with different cuts. So let's look at the blue lines, which is for all black holes. So if I derive the luminosity function, what we see is that we have an overdensity of low accreting black hole here and also here, but then when we move to high accretion black hole, we have a lake of we have an underdensity of those really powerful black holes. So there's some caveat, but it's not too bad. At least we are reproducing the black hole mass function, stellar mass function of black holes. I'm skipping this. So this was for the black hole population. So now what we can do is to select all star-forming galaxies in the simulation, and we divide these with different samples of whether those galaxies host an active AGN or an inactive AGN. So here, the process is a bit busy, but it's for different redshifts. So from redshift 4 to redshift 1, and I'm showing you the histogram of galaxy sizes. So for the green histogram correspond to star-forming galaxies with a black hole or no black hole, but at least no AGN, so no active black holes. And let's take the goldish histogram. So those are star-forming galaxies with a powerful AGN. And what we can see when you look at this distribution, or maybe you can just look at the triangles here that are the mean value of the distribution, what we see is that if you have a really if you have a really powerful AGN in orange, the size of your galaxy is smaller. So the more active the AGN is, the more compact the galaxy is, in average. And some of those star-forming AGN may be also really attenuated, and this are obscured, and this is related to the Strang et al. Paper. But the key point is that if you have a powerful AGN, the size of your galaxy is most likely to be more compact. So we can turn this around, and here again is a plot from Dell. And we can look at the same kind of diagram for the simulation. So you need to switch to twist this plot. So the star-forming compact galaxy are over there, and in the simulation, in this specific star formation compactness plot, they're over there. So here I'm only showing the most massive galaxies, but what we see is that the powerful AGN are always have a higher probability of being in a star-forming compact galaxy part of the diagram. So you can quantify this result and look at the occupation fraction in the different part of the specific star formation rate compactness diagram. So if you take this panel, which is for really massive galaxy, higher than 10 to the 11 solar mass. So this is the evolution with redshift and the occupation fraction of AGN. So you have a really high probability of having an AGN if you're a star-forming compact galaxy, so this is the red lines. But if you are in a crescent compact galaxies part of the diagram, the probability of hosting an AGN is really lower. So we can quantify this in terms of number. So this is the paper of Dell. So quiescent compact galaxy only have a probability of 10% of having an AGN. But the star-forming compact galaxy go to 40%, so half of them probably have a powerful AGN. So this is X-ray selection. So I do the same X-ray selection in the simulation. And what I found is that numbers are really higher at the first sight, but the ratio between the different populations are actually in good agreement with observation. So from the simulation, compact quiescent galaxies host almost 4% less AGN than compact star-forming galaxies. Whereas in the observational paper, it's about 4.7%. So we have good agreement with the ratio between the different population, and actually those really high number can be understood because we don't correct here for quantum thick AGN, which are AGN with really large column density, or attenuated AGN. So if we do a simple correction for this, and we assume that quantum thick AGN are about 30 or 50% of the AGN population. We actually get really good number, in really good agreement with the observational paper. So we get 60 to 40% of star-forming compact galaxies having an AGN, and we get quiescent compact galaxies of like about 10 or so % of hosting NHN. So the simulations show a really good agreement. You can even look at the distribution of this. So again, the yellow part is the quiescent compact galaxies, and the red histogram is the star-forming galaxies. And you see that with time, and this is the dashed line corresponds to the limit in terms of X-ray selection. So you see that the quiescent compact galaxy will never be detected as having an AGN, but for the star-forming compact galaxies, they will be detected as an AGN. So I didn't say it, but it's a really ongoing work. So if you have any suggestions, I will be happy to share this with you. And just to finish, I have a few examples because we talk about we talk a lot about AGN and galaxies and the role of AGN in crunching the galaxy and so on, but we didn't see, I think, any evolution with actually a simulation with an AGN in it. So I wanted to show this to you. So this is a specific star formation rate as a sigma or compactness quantities here. It's a bit busy, but we can follow in time the galaxies, and this is color-coded with redshift. So redshift 0 is really red and blue for high redshift. And the size of the circles indicate the black hole activity. So you can actually see in a nice way where the black hole activity is the highest. And here you have different diagnostics. So you have some mass quantities. So the stellar mass is in yellow. The stellar X situ mass is in red. So it's a proxy for mergers. So for example, we have mergers over here. The green mass is in, the gas mass is in green, and the black hole mass is in blue. And then you have here the star formation rate in yellow, and the accretion into the black hole is in blue, and this dashed line corresponds to the limit, the X-ray limit for detecting an AGN. So every time we are above this, we can possibly detect this as an X-ray AGN. And here is the size of the galaxy. So what happens? If I go really quickly. So here you have first a compaction event. So the gas in the inner part of the galaxy is increasing, and you have this fast increase here. So this corresponds to a minima in the size of the galaxies, but also a peak in terms of stellar activity, but also black hole activity over there. And then the gas fraction, the gas mass in the inner part of the galaxy is dropping really abruptly. And then you have quencher galaxies in terms of star-forming activity, but also black hole activity. Okay, sorry. So the peak of the black hole activity is really in this phase of compaction, in this compaction phase, and then you quench everything. And here I'm showing you a different diagram. You can pick your favorite diagram. So it's star formation rate as a function of galaxy mass, black hole mass as a function of galaxy mass, and then sigma as a function of galaxy mass. And the really, which is really nice with the simulation, is you can actually follow everything in time and see how it fits the redshift 0 in gray population. And what's the last? I should what? I'm over time? Okay. Okay. I'm just showing like a quick example where you quench your galaxy, but not totally, and then you have some more accretion into the black hole, and you have another quenching event that totally shuts down the galaxy. Thank you. Sorry. I'm over time. Sorry. So I guess my question is it important that we reproduce the ratio of the population or the population like themselves? I'm just saying that when you do the selection that I'm doing, which is selecting the most compact galaxies and star-forming galaxies or quiescent galaxies, I'm just saying that the fact that the numbers are really similar is something really strong. I'm just saying that I'm reproducing the trend that we see in the observation, meaning that in the star-forming compact part of the diagram, we have actually, we see in simulation a really high fraction of AGN, which I think is the trend that I've been seeing in many observational papers.